Assalamualaikum warahmatullahi wabarakatuh. Welcome to the fourth video lesson for physics online learning. So in this video lesson, we will continue the last time where we stopped. And in this video lesson, we will look at decay equations. There are three things that we will cover for this video lesson. So these three things are listed down here in these three learning objectives. The first learning objective and the first thing we will cover is how to use the nuclear notation. So you already know from your chemistry lessons how to use the nuclear notation. Just in case some of you forgot what is a nuclear notation, here you can see in this picture here, these are nuclear notations for several atoms or for several elements. So here you have rubidium, I think, and here you have potassium. That's for iron. The way the elements are written down, these are what we call nuclear notation. So you will learn or basically be reminded of how to use this nuclear notation, especially in decay equations. The second thing that you will learn today, and also the second learning objective, is how to construct equations for radioactive decay. So in radioactive decay, one element or one substance changes from form from one to another, and it emits radiation. And we can write down that process uh, in terms of an equation. So here you have potassium. The potassium decays, emitting a beta particle, and and what's left of it, it becomes an argon atom or argon nucleus. So you are going to learn how to write or construct decay equations later. And then the third thing that you will learn in this video lesson is we're going to talk about what happens to the nucleus when there is a alpha decay or when it gives out alpha radiation, and also what happens to the nucleus during beta decay, and also what happens to the nucleus during gamma decay. So we're going to talk more in detail what happens to the atom, why is alpha decay is a helium nucleus, why a beta emission is a electron, and so on. So like I said in the previous slide, you can write down equations to describe the process of radioactive decay. So these are on the right here, you can see these are some of the examples of the decay equations that you might see throughout this lesson. And when you write down the decay equation, you need to include several things. So these are the rules for when you write down the decay equations. Right, so the first rule, you need to include the original nuclei or what we call the parent nuclei. So this is the original radioactive isotope or radioactive substance. So in this equation, it is this part of the equation here. These are the original radioactive isotope before it decays. And then you have to write down the radioactive emissions. So these are your alpha, beta, and gamma. So these are here, and also the resulting nuclei that is formed from the decay. So this is what we call the daughter nuclei. Okay, so you have a radioactive isotope, it decays, emits a radioactive emission, so that could be alpha, beta, or gamma, and then what's left is a new type of or a new element. We are going to talk about the alpha decay first. What happens during an alpha decay? An unstable nuclei undergoes alpha decay when it gives off an alpha particle. So an alpha particle from our previous lesson, this is basically a helium nuclei, meaning it has two neutrons and two protons. Okay, so you can see in this diagram here what that looks like. So after the decay, what you are left with is a more stable nuclei, a different kind of element, if you want to say it like that. So in this diagram here, you will see in the beginning you have uranium-238. Then the uranium-238, it's unstable, so it gives out an alpha particle or a helium nuclei. That's what we call an alpha particle. And then what's left is afterwards it becomes thorium, TH, which stands for thorium. Right, so here's are some examples of alpha decay. So thorium decays into radium by emitting one alpha particle. So the equation looks like this. You have thorium and then an arrow. It becomes radium by giving out an alpha particle. So I'll show you what an alpha decay looks like with the animation coming next. Right, so here I have a simulation or an animation that shows what happens during an alpha decay. So here I have a nucleus of polonium-211. It's radioactive, it's unstable. What's going to happen is it's going to decay, giving out an alpha particle, and then it will become a new atom, which is lead 207. So I'll play this animation and you will see what happens. Right, so it's unstable. Okay, then it decays. I hope you can see that. So the polonium decays, and then it gives out an alpha particle. That means within its nucleus, it will give out 2 protons and 2 neutrons out, out in the form of an alpha particle. So you have less protons and neutrons inside the nucleus. Before, it has 211 protons plus neutrons inside the nucleus, and then it gives out an alpha particle just like that, and then so it gives out 2 protons and 2 nucleons. So it loses 4 things from inside the nucleus. So the number now, the nucleon number now becomes 207 because it gave out 2 proton and 2 neutron. So minus 4. 211 minus 4 is 207. Another example of an alpha decay is uranium. It can decay into an isotope of thorium by emitting 1 alpha particle. So the decay equation looks like that. Now the thing that you need to know, okay, so here's another example. Radon decays into an isotope of lead by emitting 2 alpha particles. So if it emits 2 alpha particles, then you will see the multiple number 2, the factor 2 there inside the equation. So here radon 222 becomes lead 214 by giving out 2 alpha particles. So that's the symbol for alpha particle, and it has a factor of 2 in front of it. Now, the thing that you need to know about the decay equations is that the numbers are all balanced. The numbers on the left of the equation and the numbers on the right of the equation, they are all balanced. So what do I mean by that? So you have the nucleon numbers at the top and then the atomic numbers at the bottom. The nucleon numbers on the left side is equal to the numbers on the left side are always equal to the numbers on the right side. So what do I mean by that? So let's look at this first example. Let's check out the mass number or the nuclear number. So thorium on the left side of the equation is 228, and it should be equal to the right side, the number on the right side. So radium has 224, and the alpha particle has 4 nucleons. So here you go, 228 is equal to 224 plus 4, right? There, it all checks out. And the number at the bottom also should be equal. On the left and on the right, they should be equal. So you have 90 for thorium, and then for radon, 88, plus the number for the bottom number for, or the atomic number for the alpha particle is 2. So there you go, 88 plus 2 is 90. So the numbers, when you are writing down decay equations, you have to make sure the numbers all are balanced. The numbers on the left, the nuclear number, the atomic number on the left should be equal to the nuclear number and the atomic number on the right. Let's check out this one here, down here. So down here is a bit trickier because you have 2 alpha particles. So we will do the top numbers first. So these number first, and they should be equal. So so you have left and right. On the left, we have radon's nuclear number 222, and then that should be equal to 14, which is for lead, plus for alpha particle, the nucleon number is 4, but you have 2 alpha particles in this case. So there needs to be a factor of 2 in front of the 4, right? 2 times 4. So 214 plus 2 times 4, 2 times 4, that's 8. 214 plus 8, that should give you 222. And the numbers all checks out in this case. As for the atomic number, or the number at the bottom, you have 86 is equal to 82 plus, there's a factor of 2. There are two alpha particles there. 2 times 2. Okay, let's check again whether this number is correct or not, or the left and right side, are they balanced or not. So 2 plus 2, that's 4. 4 plus 82, that is 86. So that is indeed, the numbers are all, the numbers on the left and the numbers on the right are balanced. So you have to keep that in mind. Okay. For beta decay, so what happens during a beta decay? During a beta decay, an unstable nuclei undergoes beta decay when one of its nucleus turns into an electron and proton. The electron is then emitted from the nuclei as radiation. So this is a bit different when compared to the alpha decay. So during a beta decay, you have protons and neutrons inside the nucleus. Because it's unstable, what happened is one of the neutrons turns into an electron and a proton. And I will show you what that looks like in the animation. Okay, so this is the animation that I'm talking about, or the simulation. Here we have hydrogen 3, or otherwise known as tritium. And you can see there are 3 nucleons. In other words, there is 1 proton, that the red one is proton. The gray ones, those are the neutrons. So there are 2 neutrons and 1 proton for hydrogen 3. And then we will see, and it will give out, it's unstable, it will give out a beta radiation, or beta particle, and it will turn into helium 3. Okay, so it will turn into a new nucleus, a new atom, a new element, in other words. Okay, so let's play and see what happens. So bear in mind, the red is proton, and then the gray is neutron. Okay, so it decayed, right? It becomes helium. Now, as you can see, before we had 2 gray neutrons here, 2 gray particles, those are the neutrons. And then what happened is one of the neutrons become a proton. It then becomes red, and it gives up this blue ball here. I hope you can see this blue ball. That's the electron. And this red ball, that's the proton. Okay, so one of the neutron changed into a proton and an electron. The proton stays inside the nucleus, while the electron is ejected outwards. That's the beta emission. Don't worry about this. That one is not in the syllabus, so don't worry too much about that. So you just have to focus about these two. Okay. So let's look at that again and see what happens during beta decay. Let's look at that again, but this time pay attention to this particle here. And then it should decay soon. There we go. Okay, it turned gray, from gray to red. In other words, from neutron to proton and electron, but the electron is ejected outwards. So that is what happens inside the nucleus during a beta decay. What does the decay equation look like for beta radiation or beta decay? So we will see. These are some of the examples. An isotope of argon is the result of a radioactive decay of a potassium nuclide. So here we have potassium, and then the potassium changed to argon, giving out a beta particle. An americium nucleus decays into einsteinium by emitting 4 beta particles. So americium becomes einsteinium by giving out 4 beta particles. So there's a factor of 4 you can see here. Oops. There's a factor of 4. So that's 4 times the beta particle. And similarly to alpha particles, the numbers on the left side of the equation and on the right side of the equation should equal or should balance out with each other. So let's take this one as an example. Let's take the numbers at the top, or in other words, the mass number, or otherwise known as the nucleon number. So the nucleon number for potassium is 40. That's the number on the left. So that's the left side of the equation. Now onto the right side of the equation, you have argon, which also has 40 nucleon number for its nucleon number, plus, and the nucleon number for a beta particle is 0. So as you can see here, the numbers on the left and the right, they are both equal. So 40 plus 0, that's equal to 40. Now let's look at the numbers at the bottom, or the atomic number. So for potassium, it's 19. And then argon, it has a atomic number of 20 plus, here we go. So for the beta particle, it has an atomic number is -1. That's because it's an electron, it's negatively charged. So it's in other words, it's the opposite of a proton. So you can see here 20 plus minus, or 20 minus 1, that should give you 19. So um, for a beta particle, the difference is we have a -1 in its atomic number. So 20 minus 1, that gives you 19. So let's check for the second example, americium, einsteinium. The top, as you can see, is 243, the nucleon numbers. 243 is equal to 243 for einsteinium. They have a similar nucleon number. And for the beta particle, it has zero nucleon number, but there are 4 beta particles. So 4 times 0, that's basically 0. And 0 plus 243, that should give you back to 243. Okay, so both sides of the equations are balanced. For americium, we'll look at the numbers at the bottom now. For americium, the bottom number, or the atomic number, is 95. Einsteinium, it has an atomic number of 99. And then for the beta particle, it has an atomic number of -1. But there are 4 beta particles given out in this process. So it should be times by 4. So 4 times -1, that's -4, -4, 99 -4, that should give you 95. So in both cases, the equation is balanced, or the left and the right side of the equation are both balanced or equal. Now let's look at gamma emission. So gamma emission, this is rather simple. What happens during a gamma decay or gamma emission? So as you remember, gamma radiation is a high energy electromagnetic radiation. So there are basically no changes to the nucleus when it comes to the number of particles. What happens is one of the particles just gives out a gamma ray. So after an unstable nuclei has emitted an alpha or beta particle, it sometimes has surplus energy. This energy is emitted as gamma radiation. So basically, inside the nucleus, one of the particles is very energetic, and then because it's very energetic, it will give out this energy as gamma radiation, or a gamma ray, and therefore we have gamma radiation. In terms of the radioactive or decay equation, what does that look like? It looks like this. So I'll give you an example. Let's look at this example here. I think that's polonium. Correct me if I'm wrong. I'm not a chemist, but I think it's polonium. Pa, which stands for polonium, if I am correct. 234, that's the nuclear number, and then 91, that's the atomic number. It has a star there. That means that this polonium here, it's very energetic. It's excited, as you can see. Excited in what we mean by excited, it has a lot of energy. It's the same element, but it has a lot of energy. And then it becomes a normal polonium, or in other words, a low energy polonium. It doesn't have a star anymore at the top. The rest are all the same by giving out gamma radiation. That's the symbol for gamma radiation. And remember, the gamma radiation is just energy or an electromagnetic wave. So it has 0 nucleon number and 0 atomic number, 0 proton number. And as you can see, all the numbers are balanced. So this is an example of a gamma decay equation. Some radioisotopes give out more than one type of radiation. For example, it can give out alpha and beta together, or it can give out all three, so alpha, beta, and gamma. So we will look at that next. Here's an example of what I'm talking about. A uranium-238 nucleus decays by emitting 2 alpha particles and 1 beta particle into an isotope of actinium. This is the decay equation of what that looks like. So uranium-238 becomes actinium-230 by giving out 2 alpha particles and also 1 beta particle. So if you check out the decay equation for this one, the numbers on the left should be equal to the numbers on the right. So I'll quickly write down what those numbers look like. For the mass number of neutron or nuclear number, this is what it should be. It should look like. Okay, that's the mass number. And for the atomic number or proton number, it looks like this. And the left side of the equation and the right side of the equation should balance out for both cases. Okay. And that's the end of this video lesson. So to recap back what we learned about the decay equations. When you are writing decay equations, make sure it is complete. In other words, or make sure it's balanced. In other words, the numbers on the left side of the equation should be equal to the numbers on the right side of the equation. We looked at what happens to the nucleus or inside the nucleus during during alpha, beta, and gamma radiation. So during alpha radiation, what happens is the nucleus will give out 2 protons and 2 neutrons. So that's in the form of a helium nucleus. During beta radiation or beta decay, the nucleus, one of the neutron becomes a proton and an electron. The proton stays inside the nucleus while the electron is given out as the beta particle. And then for gamma radiation, there are not a lot of changes in the nucleus. It's just probably one of the nucleon or one of the neutrons or protons are excited, and then it gives out is excitement, it gives out this energy in the form of a gamma radiation or a gamma ray. And those are the things that we talked about in this video's lesson. Next video lesson, we will learn about half-life. So I will stop the video today. I'll see you next week. Assalamualaikum warahmatullahi wabarakatuh. Thank you for watching.